Hi guys. Today we'll be looking at the bias-variance trade-off and trying to understand some of the intuition behind it. I feel like this is a topic that's it's really explained in a way that's easy to understand. Especially, it took me really long to understand why it's called bias-variance trade-off. So let's dive into this. Um, so we're going to import NumPy, actually not pandas today, just NumPy, PyPlot, and Seaborn, and we'll use a linear regression model for showing um, how different models fit differently to data. So let's go ahead and import all of this, and first thing I want to do is generate some synthetic data. So we're not using a real data set today. The reason for that is I need access to the signal that generates the data. So I'm going to create the signal myself. So the signal is sort of like the master behind the scenes that's actually causing the data, right? So we don't know the signal in a real setting. So this is more of a theoretical exercise, but it's a way of understanding how a model works in the general sense, given any sort of data. So let's create a function called generate data that's going to take in an x. The x is going to be the x values, and then this is going to spit out the y values so that we can plot them. And we're also going to pass in a noise threshold. And we're going to default this to 0.5 maybe, or 0.1. Alright, so we're going to create the signal, and this can be anything you want, any sort of function. For example, let's do a simple line, right? So mx plus b, let's use the slope to be 1.5, that'll be times x, and then we'll add b, which will be 0.5, that'll be our intercept. Then we just return signal. So this is pure signal with no noise, and let's plot what this looks like. So I'm going to create some x values. This is just going to be random values. Let's use between 0 and 10, but that can be anything. So I'm going to use numpy.random.uniform, which will just generate uniformly sampled values between 0 and 10, and let's just do 100 of them. Then we'll create our y values, and this will just take x and pass it into our generate data function. So x equals x, and our noise threshold, for now, it doesn't matter. Let's just set it to 0. And we'll plot this real quick. So we'll make a new PyPlot figure in a 10 by 10 figure size. And we'll do a scatter plot where we'll plot the x's on the x-axis and the y's on the y-axis. So here's the data generated by the signal. And you can see it's perfectly signaled. There's no noise. You can literally just see the line there. That for the signal is the line that generated it behind the scenes. So we can actually plot the signal. It's the actual signal. Why don't we do that? So under the scatter plot, I will create this signal x, and this will be a linear space because we want it we want equally spaced points for the y. So what I'm going to do is a linear space, again between 0 and 10, and we'll just pick 100 points. And then we'll create our signal y, which will be generate data again. For this, we had to make sure the noise threshold is 0 because we want this to actually show the signal. And here, instead of x being x, x will be signal x. And then we have to plot it. So plt.plot signal x on the x and signal y on the y. And let's just give this a color as well. I'll make it cyan. And you can see that's the signal that generated the data. Now I actually want to put this before we plot the scatter plot, because the signal, actually it's not plotting the scatter plot on top of it. Oh well. The signal is behind the data, right? The data is sort of a result of the signal. So the cyan line is the signal, and the data is generated from it. Now, in a real-world setting, you don't know the signal. It's some arbitrarily complex function that's generating these data points. But let's add some noise now. So the noise is just going to be a slight deviation from the signal. So what we're going to do is to generate this, we'll just use a random a standard normal random variable to generate some error terms which we can apply to generate noise. So we'll do numpy.random.normal, and we want a standard normal, so that's a mean of 0, standard deviation of 1. And the size, which is the number of samples to generate, will be, we want the same number as x, so let's just make it length of x. And then I want to scale this noise down by the noise threshold. So in this, noise threshold. So if we have a noise threshold of 0, we don't have no noise. If we have a noise threshold of 1, we have 100% of the original noise generated. Noise threshold of 2 would be twice as much noise as originally generated. And then we're going to return signal plus noise. So right now we have a noise threshold of 0. So let's go ahead and change this to a noise threshold of 0.5. And you can see some noise has been generated. So the signal stays. The signal is no noise, right? That's what's generating this data. But the more noise there is, the more dispersion from the signal there is. So let's imagine that we bump this up to like 5.0. Then there's hardly any data clinging to the signal anymore, because there's so much noise in this data. So we're gonna I think we'll stick with maybe 0.7 sounds good. And so the question is, how do different models fit to this data in relation to the signal? And especially as the noise generated by the signal changes, what happens to the model's fit? That's the question that's being asked when we're looking at this bias-variance trade-off. So the first thing we're going to do is look at a high bias, low variance model. So if you're familiar with this would just be like a simple linear regression, a model that's very simple and not able to capture a lot of the complexity of a more intricate signal. So because I want to demonstrate this with a linear model, it doesn't make sense to have a simple linear signal. So why don't we make the signal a little more complex? What I'm going to do is add a sine of 2x term here. And, so numpy.sine. And now you can see the signal has this sort of cyclical nature to it. So now we'll be able to basically see how a linear model compares to this. So let's start by creating just one plot. So what I'm going to do is first we'll generate some data. So we'll create x. This will be numpy.random.uniform. Just like we did before, just generating random x values between 0 and 10. We'll get 100 of them. And then y, we'll use the generate data function, passing in x and setting a noise threshold. Let's make it 0.7 again. And we'll do a scatter plot. Should probably do a figure up here. Let's do a 15 by 15 figure. And for the scatter plot, x equals x and y equals y. Also change the size maybe. Okay, so actually it's pretty big. Let's bring it down to 5 by 5 for now. Yeah, and we'll do plot.show. Okay, so you see each time we generate this, the noise changes, right? But the signal stays the same. So what we want to do is fit a linear model to this data. So after we've generated the scatter plot, I'm going to create a new linear regression model. And we'll fit it to just this single x vector. So this only has one feature, which will just be our x's, which are just random numbers between 0 and 1. However, we need it to be two-dimensional, so I'm just going to use numpy.expand dimensions along axis 1. So we just give it that extra dimension. And then the y is just going to be our y. Okay, so the model's been fit, you can see, but now we can access the model's parameters that it learned using model.coefficients to find the slope term, and model.intercept to find the intercept term. So let's go and plot a line using the slope and intercept that was learned by the model. So what we're going to do is create some new data to plot this line. I'll call it fit x and fit y. Fit x will just be another linear space, numpy.linspace. So we'll just provide equally spaced values between 0 and 10, so 100 different ones. This is just to create that sort of space for our line to live in. And then the y values, which is going to give it the linear shape, will just be taking the fit x and multiplying by the slope term, which is model.coefficient, .coef. And then we're going to add the intercept term, so plus model.intercept. And now let's plot this line. So plt.plot, so fit x and fit y. Let's also give this a red color so we know this is our model. And you can see this is the line that was fit by the linear regression. Right, so let's also take a look at the signal in relation to it. So I'll grab this and I'll just paste it in. Before we even generate the data, I just want to plot the signal first. So you can see the signal and you can see the fit. And in this case, you can notice that the fit really fails to capture the signal. It's a very simple fit. It can't capture that sort of sine wave nature of the signal. And we'll get back to this in a second and why this is called a high bias, low variance model. But before we compare, let's also get that high variance, low bias model. Okay, so for the high variance, low bias model, we're going to need something more than just a linear fit. So what we're going to do is generate polynomial features so that this red line can actually be more complex, be a very complex polynomial. So for that, we're going to need a function which I'm going to call generate features. This is going to take in an x and a degree, so a polynomial degree. And all this is going to do is basically stack together the original x along with the x squared, the x cubed, the x to the fourth, x to the fifth, up to whatever degree is. So what we're going to do, right now x is just this random random array of numbers. If we square it, you get the squares of it. If we get the cubes, we get the cubes of it. We want to put these all together into a single matrix that we can use to train our model on. So what we're going to do is create a new list comprehension that's x to the I for I in range, let's say 3. But actually, I don't want x to the 0, so I'm going to do a range from 1 until 3 plus 1. So this would be of degree 3. This will return 3 columns, or rather 3 arrays. The first one will be x to the 1, so just x. Second one will be x squared. The third one will be x cubed. And you can see they're all separate numpy arrays inside a list. So what I want to do is make it into one numpy array. So we're going to use numpy.stack to do this. And let's just look at the shape of that. It is now a 3 by 100 stack numpy array. However, I want those dimensions flipped, so I'm just going to transpose it. Now we have 100 by 3. And so this is valid feature data. Here the first column is the original x, the second column is the x squared terms, and the third column is the x cubed terms. So what we're going to do is use this inside our generate features, except instead of 3, we just pass in whatever degree we want. So this will generate this new feature matrix based on some original feature vector and the degree of polynomial features we'd like. So if we want generate features, we'll just use the x we have from before, and let's say degree 10. You can see, let's just look at the shape of that. You can see it generates 100 by 10, where each one is the original x raised to some exponent. If we did 100, it'd be 100 by 100. If we do 2, it's just 2. That would just be x and x squared. Okay, so because we have this, we can now fit a more complex model. So what I'm going to do is I'm going to set a degree. Let's start with 1. Degree 1 is the same case as over here. So we're going to let's plot the signal again. So let's just go up here and grab this part. In fact, we can just grab all of this. Okay, so we create a new just show. So this is what we had before. We haven't fit the model yet, but this is just noise generated by some signal. So what we're going to do is, after we plot the scatter plot, we're going to create a new model, which is linear regression. But this time, instead of fitting on just the single feature called x, we're going to fit on all of these polynomial features. Why don't we bump degree up to 3, so that we have 3 different features, which will be x, x squared, and x cubed. So we want to create this new matrix of polynomial features, so I'm going to call that capital X, and that's going to be using the generate features function we created that takes in the little x and a degree of size degree. Then we create the model, and we fit the model on the big X and Y. Okay, so now we want to plot the red line. That came from this. However, this time, instead of just multiplying the single coefficient value with the fit x, we're going to do a matrix multiplication so that, well, actually what we should do is create this big fit x, right? So fit big X using the generate features again, using the same degree. Instead of x, we pass in fit little x, and this is creating, this is just to plot the model's coefficients, right? So it has to be the same dimensions as the coefficients of the model. So here, before we just multiplying this single coefficient by by this linear space, in this case, we're going to use matrix multiplication to use this big fit x. Let's look at this. Just look at big fit big X, and look at the shape of this. It's 100 by 3, so we have 3 features, and the model. Did we train it? Yes. The model's coefficients are now 3 different values, 1 for each feature. So what we're going to do is matrix multiply this so that this value gets multiplied by the first column of fit x, this value gets multiplied by the second column of fit x, and this value is multiplied by the third column of fit x. So we're going to use numpy.matrix multiplication, that mul, passing in fit x, the big X, this one, and model.coefficients. And that will result in a new matrix, a new vector of size 100. And this will be the y value for each of the original fit x values. Okay, so just to show the graphical interpretation of this, let's put this in here. We now have this matrix multiplication, and we also should add the intercept on, so model.intercept. Okay, now let's plot this. Alright, and you can see the plot. So we are using degree 3, so you can't really see what's going on here. Let's bump the degree up, I think, to 13. And now you can see the model is now able to capture a lot more complexity because it's using these polynomial features as input. Okay, so now we have these 2 different types of models. This is a high variance, low bias model, and this is a high bias, low variance model. And to demonstrate why these are called this, I'm going to plot a bunch of them. So I'm going to go up here, and I'm going to create a for loop. We'll plot 9 of each. So for I in range 9, we'll create a new subplot in a 3 by 3 grid indexed by I plus 1. And we're just going to bump that over. And I think I'll change the figure size up here to 15 by 15. And I think that's it. I'll also give it a subtitle. Plot.subtitle. I'll just give a title to all of the subplots. High variance, low bias. This is high bias, low variance model. Okay, and now we can see, let me zoom out a little, we can see different types of models, the same type of model, right, just a simple linear regression, but as we can see what happens as the noise generated by the signal changes. So in each of these we have different noise, right? The signal's the same, the cyan line is the same, but the blue dots are different. The noise is different. And you can see that the red line doesn't really change much as the noise varies. So let's also take a look at this in the context of the other type of model down here. So I'm just going to do the same thing, bump this up to 15 by 15, and indent this. And I should give it a subtitle as well. So this is a high variance, low bias model. We can look at what's going on here. You can see this time the fit hugs the signal a lot more closely, but it changes much, much more depending on the noise. Right, so we have a lot of different red lines, whereas up here all the red lines are the same. So now we could really sort of understand why this is called high bias and high variance. So let's start with bias. Bias usually means error or difference or distance. And the reason we have a high bias in this model is because as we vary the noise generated by the data, the bias between the fit and the signal is high, which means the fit is not able to hug the signal very closely. Right, so there's a lot of distance between the cyan line and the red line. You can see there's all these gaps there. Whereas down here, this is low bias because the average fit hugs the signal very, very nicely. So as we vary the noise generated by the signal, the fit hugs the signal really well. So this is high bias because there's a lot of distance between the fit and the signal as you vary the noise. And this is low bias because there's very little distance between the fit and the signal as you vary the noise. So now let's look at variance. This is a low variance model because as you vary the noise generated by the signal, the fit does not change very much. We have the same straight red line every single time, and as we change the noise generated by the signal, the fit just sort of stays as that red line. It does not vary. It has a low variance. Whereas down here, as we vary the noise generated by the signal, the fit changes substantially. So you can see we have all sorts of different fits here as a result of how the noise happened to be generated. So over here, we just have a sort of a pretty good fit. I'd say it's hugging it really well. But over here, we have these big ends coming off, and you can see it's all sort of depending on what the noise is. So this varies a lot. So the actual fit varies as the noise generated by the signal varies. So this is high variance. Whereas up here, the fit does not vary very much as you vary the noise generated by the signal. So this is low variance. Alright, so I hope this helps you understand the bias-variance trade-off. Every single model has some amount of bias, some amount of variance just built into the model's capabilities. For example, tree models have a very high variance because they're really good at fitting to individual training examples, whereas these linear models tend, especially if you're not using polynomial features, to have a very high bias and low variance. Alright, but that will sum up the video. Thank you so much for watching, and I hope you have a wonderful day.